There you go. That works much better. Turn off the front light. That's up there. Okay, I'm just going to kind of pick up where I left off. And I know that if you watch the recorded video, I'm probably repeating some slides, but I got kind of a gut feeling that some of you have not watched that video, so I'm going to go ahead and repeat these slides because we've got plenty of time, as it turns out. Okay. Well, we're kind of alluded to is that we kind of talked a little bit. I'm backing up here a little bit up there and get into the internal electronics of these ICs here and kind of up there. Let me back up. All right, up there. Okay, when we look at digital ICs, you'll hear these terms thrown out a lot. Small scale integrated SSI, MSI, LSI, VLSI, ULSI, and giga scale integration. Actually, the last three you don't hear. Most common is VLSI, very large scale integration. That is probably not that many of the chips today. They still use that terminology for a lot of the chips. However, a million gates is not considered that high of integration. I mentioned the other day the Altera device that I had on that board that I brought up there. That was not a very large device. It had about 250 pins or something on that. I can't remember. We'll see that again. And I'm still working on moving us to a lab for our Thursday class. Thursday class. That's there, so that we can start doing some labs that there. However, most chips today, when we start talking about microprocessors or even microcontrollers, are starting to talk a million gates or more. Out there. And when we look at the circuits that we've been looking at thus far, the largest circuit we've been looking at is 10 gates, 15 gates. So obviously the design techniques we're using probably will not work very well when we're talking about circuits that are a million gates or more, and we're using Karnaugh maps that are designed to design circuits, for 10, 15 gate circuits. So we won't get into much of the other design techniques, but I want to talk a little bit about that up there. And these slides may not cover them, but I will go into them in more detail up there. Some of the newer design techniques. Hardware-wise, when we look at older TTL type chips, the SSI chips, the small scale integration, or even the medium scale, the DIP or the dual inline package right there is the most common in older equipment that's been around. You look down at someone at the door there. Because I keep looking, you're catching out the corner of your eye. I'm thinking someone's staring into this room, giving me funny. I've been known to do that to other lecturers back to the U.S. Stare at the door and make funny faces at the instructors just to see if I can throw them off balance. That's there. But the DIP package is still used in a lot of universities. If this class was taught in a technology program back at my old school, we would have you do a final project which would have like 15 or 20 DIP chips on there with a spaghetti's nest or a rat's nest of wires connecting them all up. That's not practical in real life today. I mean, we still use the proto boards for some things that there, but for industrial prototyping, I haven't done that in a long time. We usually use a green wire, and we use the actually doing printed circuit boards has gotten cheap enough for a lot of the prototypes. We'll just go ahead and run a circuit board right there, and we'll talk a little. All right, there we go. The pins are numbered, and this is something that I'm going through this, even though we're not going to do it in the labs in this particular class, but this plays into all your labs. Because if you look at analog parts, they follow the same notation. This is a standard numbering package for for all electronics chips, electrical chips, ICs, whether you're talking digital or analog. So if you're talking a LM741, a LM7805, which are linear chips that they follow the same package that there. You have, as a matter of fact, I shouldn't use this red thing that doesn't show up in the recording, but in the bottom left-hand, right, your left-hand corner there, you usually have a dot that's there, or you'll have the notch. Some may have both. Some have one or the other. That's there. That is pin 1, and they wrap around. Some people think that it goes 1, 2, 1, 2. Bottom, top. But they go 1 through 7, and then around the corner, and then 8 through 14. Now, if we're talking other types of chips, and I didn't look at these slides. Here, let me just. That's there. No. That's there. If we have a chip that's got pins all the way around, like the chip that was on the board that I brought up, the Altera chip, it's got pins all the way around. That's there. And so there would be pins along the bottom and the top, and those are usually square. And most of those, the ones that are square, are typically not through holes. That's there. And one of the things to point out is this package right here. That's a through hole. Through hole means that these pins, and I'm going to go ahead and just kind of point out, these pins right here go through the circuit board and they're soldered on the back side. Now, if you're using the prototyping board like you might have used for your electronics courses, you push those into the board, right? And then you put the wires to connect it to other circuits right there. That their through-hole technology for most modern electronics is going away. You don't see that in typically produced products. If I opened up this laptop right here, I would probably see very few, if any, through-hole parts on that. They are just disappearing. And the reason is that they're too large. That's it. If you look at your cell phone, you won't see any through-hole components in that. But if you open up, say, your microwave oven at home, you might see some. That's it. So as electronics has gotten smaller, this technology has gone away. And later on, we'll look at what they call surface mount. And surface mount means that you basically place a part on top and it's soldered to the top of the board, and the connections are done through the top and bottom and the intermediate layers of the board. This is not a course on board layout or electronic fabrication, but an older type, when I first started, a dual layer board was considered complex. When I say a dual layer board, means that you've got circuits drawn on the top of the board and the bottom of the board. Nowadays, a 10 or 12 layer board is not uncommon, where you've got layers in between that connect the circuits. That's there. And then there's connections made between the various layers. So you have the surface mount and you have multiple layers of the board, because the boards have gotten much denser. This chip is showing a 14-pin chip. All the chips we've talked about thus far, the AND gates, the OR gates, are all 7,400 parts. Those are all 14-pin chips. The programmable logic chip that I brought in the other day, that had well over 250 pins on it. Well, if you have 250 pins, that means you've got a lot of electrical connections to make into a very small area. So 2 layers is not enough anymore. So that's a challenge for the circuit board designers. And I will be real honest in saying that I am not a good circuit board designer. I've laid out circuit boards, they've worked. I've laid out circuit boards, they worked, and they failed FCC testing because I laid them out sloppily and ran clock signals around the outside and did things the lazy way. There are people that do circuit board design better than I do. I understand the technology, I understand how to do it, and I can lay out a circuit board. I'm not the best person for that job. And I remember working for a guy one time when I did a very short, very small PC board layout. And he says, I'm glad I didn't hire you to be a PC board person. I said, no, I'm not a PC board person. I can do the design, I can draw the schematics, I can write the software, but don't ask me to lay the board out. That's not that's there. And that's almost an artist skill. I'm getting a little bit sidetracked, but that is a area of electrical engineering or electronic engineering that does have its experts in that area. I had a student of mine a couple of years ago who worked for me after he graduated, when I was working on some projects, and he was extremely good. He could sit there and spend 6 hours looking from a computer and get the perfect layout every time. I would look at that circuit and I would spend 30, 40 minutes and I'd be done with it because I don't have the patience. And of course, my layout was not near as good as that there. So it is one of those skills. But all I'm trying to get across is this technology is a little bit older because back with these, you could be like myself. When I learned to lay out circuit boards, we had 14-pin devices and there were 2-layer boards. It was easy to do. Nowadays, with 15-layer boards, 12-layer boards, it's a lot harder. Okay, this is what you see inside the chip, right there. And this particular set of slides kind of goes into a little bit more detail here. In Malaysia, there are multiple companies that do exactly this work right there. The actual silicon chip is manufactured in what they call a fab. A fab, essentially what it does is takes a big circle, and let me pull up my pen and just kind of draw. Again, I'm not an artist, but I'm going to take a little side note here and talk a little bit about the fab process. We take silicon is made in actually a large cylinder. That's supposed to be a cylinder, something like this coffee cup right there. It's a cylinder that's there, and then it's cut into wafers. And each wafer right there, and then if you look at it from the side, what happens is we place a mask over it, and we expose it with a gas. And this gas sets up pockets of what they call positively charged material or negatively charged material. Then we place another mask on it, and we repeat the process. And we keep doing that until the circuit is on the chip. Now, this piece of silicon actually is going to be cut into small little chips right there. The pieces that are not complete, of course, are thrown away. And each one of these is a particular circuit right there. So this is a process that is done in a fab. I'm not sure how many fabs there are in Malaysia. There may not be any fabs because I have not actually visited any fabs here. I know that Singapore has a number of fabs, Taiwan has a number of fabs, the Philippines has a number of fabs. I'm believing there are Freescale, I believe, still has a fab there in PJ, Thailand Jaya. Texas Instruments just has a packaging plant. Altera has a fab up in Penang. I think Atmel has a fab. So a lot of this work is done in Malaysia of actually making the chips. Texas Instruments, my wife's niece's husband works there, and they have what's called a packaging plant. And the packaging plant actually is the one that takes and cuts the wafers into the chips and places it inside this package. And you've got these little wire bonds that go between the actual chip here and the pins there. Right there. There's a little wire bond here. You see these bonds right here. And I don't know what's going on here. That's there. But these bonds here are about the size of a human hair, depending on that's there. And this is all automated. So a lot of this work is done here, right there, in KL, right there. So, but this is what's inside the chip. Now, depending on the chip, and that there, I used to have, and I haven't seen any around here, the old EEPROMs where you could actually see the silicon wafer inside there, because those used to be exposed there, up there. But this is what's actually inside of our chip. So when we look at a chip, it's actually very, very small, the actual silicon up there. And this is where all the work is being done. And why is my pen not doing anything? Well, I must have disconnected it. Okay, up there. This is the more common package. These are using the J-shaped leads. If we were to look at there, it's a little U here that folds under that there, and then it's soldered to the board right here. It's placed on the board, and a little solder is placed right here to connect it to the board right there. And as you look around here, these are my bevel. This is here's my dot. Pin 1 happens to be in the middle here, and you got to watch these chips carefully where pin 1 is. The bevel corner usually shows you how to mount this into a connector. This particular chip there, this is an older Altera chip. This is the one I used on the board that I designed a number of years back. There, we actually placed a socket on the board and used through-hole technology to mount this to the board, but it had to go into a socket right there. Yeah. As you can see, we got far more than 20 or 14 pins on this particular one. But that's a different type of, this is a PLCC. PLCCs are not that common today. They were common probably 10 years ago when Greg Moss, he added this part of that there because we worked on this here, added that there. PLCCs are actually going away too. They're still too large right there. Okay. This is old information. When we talk about digital chips, we have a whole series of families, and this goes through 5 of them. The standard TTL, the Schottky TTL, the low power Schottky TTL, the advanced Schottky, and the advanced low power. That's there. The difference between each of those really is speed and power dissipation. Right there. When we look at an LS part, it's a low power dissipation. When we look at an S part, it's a high speed. That's it. Now, as a technician, if you're repairing something, sometimes staying within the same family makes a difference. Sometimes it does not. If the engineer that designed the circuit did a good job and used synchronous design techniques and did not push the speed limit of the circuit, of the components, then it doesn't necessarily matter that much. However, I've worked on circuits and I'm very familiar with systems that work beautifully when you have 74 parts in it, 74XX parts. 74XX parts became obsolete because that was the old school. Faster, lower power parts came out, so they quit making the 74XX. Someone dropped in a 74S replacement. The circuit quit working. It would not work. And the reason was that the part was too fast and some of the glitches would cause problems out there. So, but a 74LS04 and a 7404, which are both hex inverters, are pin for pin compatible. You could pop one out and pop right back in the circuit, and it theoretically will work. In reality, it may not work. It all depends on how close to the specifications the designer did that. How wide of a glitch that he allowed to be in the final circuit. That's there. If there was no glitches and the circuit work was well designed, you could pop in the fastest chip in the world. But theoretically, you should always be able to go from a 74 to a 74 ALS and not have problems. But some circuits, you will have problems. Okay, this is a complicated circuit for your stage, right? That's it. But what we're looking at here is this is a typical TTL inverter, and what we've got here is this is what they call a push-pull output right here. This circuit on this right here, this happens to be a Class B push-pull amplifier right there. And this has a transistor on there. And so what we have is, if we put a 1 in here, we're going to get a 0 out here. This inverts. This is an inverter right there. This is a TTL part, which means it's transistor to transistor logic right there. Get there. So this is what we see inside. So a single gate requires 1, 2, 3, 4 transistors and 2 diodes. That's it. This is the last class that you're going to see put this circuit up here. I'm not going to, we're not, this isn't a course in analog electronics. You probably have seen circuits similar to this if you look at Class B amplifiers in your electronics course. Have you had a course in analog electronics where you looked at transistor amplifiers? No? Okay. Do you even know what a transistor is at this stage? No. Okay, then we will skip through this right here. So there's another series of components called the metal oxide, CMOS, right there. Again, I'm going to kind of go through this. That's a different type of chip. CMOS is a FET, a field effect transistor. It replaces transistors for the most part. Most digital electronics are CMOS today. Right there. So you will see part numbers that say 74HC, AC, ACT. Those are pin compatible but not electrically compatible. Those are not interchangeable. That's it. Now some are right here, HCT, high speed, pin compatible, electrically compatible, and that's questionable. You always have problems if you replace a part with another part that's different. That's just, the electrical characteristics are not going to be the same. They're not going to operate at the same speed, they're not going to draw the same power, they're not going to put out the same amount of power. They are all a little bit different. Again, this is the circuit. Since you haven't had your course in electronics, I'm not going to go through this. Okay, let's go through some terminology that you do understand, or will understand here. Inputs that are not connected to anything are said to be floating. So in other words, if I leave an input unconnected, it's a floating input. Floating input typically will float high in TTL. If you measure it with a voltmeter or a logic probe, it usually doesn't say, but usually if you leave an input floating, it's going to look like it's a high. It's going to appear that there's a 1 there. Right there. Floating CMOS can cause overheating and damage to the device. That's it. So, typically, if you're designing a circuit, the rule is that you tie all inputs, either high or low, whether you're using them or not. That's just a TTL, it doesn't really matter, but CMOS, and I just made the comment that 90% of digital electronics are CMOS, therefore we should tie them either high or low, right there. That's just a general rule. Like I said, even if you're not using that particular gate, right there. Difference is a lot of the programmable logic, you're automatically tied low, that there, that internally. I think I talked a little bit about these before. Right there, these are our logic levels up there. CMOS has a little bit different range, but when we look at TTL, generally our rule is between 0 and 0.7 or 0.8 is considered logic 0. Between 0.8 In 2.0, we're looking at no man's land, or we don't know what it is. And if we look between 2 and 5 volts, it's considered a high. Our range is a little different on the CMOS because it's got a crossover voltage of 1.5 and then 3.5. So its range is a little bit more equal, top and bottom. That's it. It's one of the advantages of this. Okay, this gets a little bit into the circuit board design, or the design part of that there. Whenever if you're going to lay out draw a circuit with a CAD package, and we won't be doing that in this class, unfortunately, but if you're going to use a package like OrCAD or Multisim or Ultiboard to design the circuit, typically you would assign a part number to every IC in the chip. If you look at a typical schematic, you will see that every part number has a part number on it. In this particular case, we've got 2 parts showing, Z1 right here, which is a hex inverter. Now, a hex inverter has 8 inverters on it. So those inverters, that's there. So we have to have a way of knowing which part number that's there. So here, the first time I draw this, right here, this is the first time I draw it, I show my 5 volts and my ground right there. And that's pin 14 and pin 7. This is pin 1 and pin 2 right there. So right there. Now the second time I draw that part, I don't need to show the repeated pin 7 and 4 again. The reason you do that is because when you draw this circuit in a design package such as, I'm going to say Cadence or OrCAD, and I know that you've never seen the software package, but it's a software package that a designer will draw what their circuit's going to look like. Yeah, that's it. You might have seen, did you use electronic workbench in any of your classes thus far? You have not used electronic workbenches? Have you used PSpice? Have you done any circuit simulation? Yes? What software did you use? What's that? Multisim. Okay, I'm sorry. Multisim used to be called electronic workbench. Okay, that's my fault. I'm old and I don't keep up with the new names. But electronic workbench is now called Multisim. So you have used Multisim. That's it. Multisim, the company that makes Multisim, makes another package called Ultiboard right there. And Ultiboard is used to lay out PC boards. That's it. Multisim is used for simulation and drawing schematics right there. So if you were to go through the process of actually building the circuit and laying out a PC board, you would do this in Multisim. Since you're only using Multisim for simulation purposes, and you have no intention of building a PC board and commercially producing it, you can skip this process right there. Same thing as if I was to use OrCAD, for example, and OrCAD has been bought by a company called Cadence, so again, I do the same thing with OrCAD. That's the old name. Cadence is the new name. If I was to lay out that circuit, I could do it for simulation purposes only and forget all this stuff and not worry about pin numbers. But if you're going to be going to the next level and you're actually going to be building this board, then you're going to want to put these pin numbers on there. So this is here, this denotes right here that this is Z1, and it's usually not usually Z, I can't even remember, I'm drawing a blank what you would normally use for an IC, but it may be IC1, IC2 or whatever. But every part And you would do that for like R1, R2, C1, C2. Every component on the board has a part number right there. So it's one of those cases that but it's a little bit different when we talk about digital circuits, because a digital circuit will have multiple gates that are exactly the same inside the same component. Now you can see the same thing in analog circuits, for example, and I'm assuming since you haven't, no one talked about transistors, have you looked at operational amplifiers or op-amps? No. But an op-amp is an amplifier that goes onto an IC. And the most common operational amplifier is one called an LM741. It's been around for 30 plus years. They were around when I first started, and they're still being used. Well, there's also a component out there called an LM747, which is not an aircraft, but it's a IC that has 4 741 op-amps on it. It's a quad op-amp right there. And you would have to do the same thing right there. So, but each component there, so you would have the pin numbers located. And the reason you do this is because Ultiboard can read the multi-sim file that's there. And when you bring the circuit into Ultiboard, then you can start laying out where you want the ICs to be on your board, how you want to draw the connections on the board. That's it. So it provides a path from your circuit drawing in multi-sim to your PC board layout in Ultiboard. That's there. And the same thing with OrCAD. They've got a program called Capture or Schematic Editor where you draw the schematic, and then you can lay out the PC board layout. Ultiboard and multi-sim are typically used in university settings. In industrial settings, Cadence or OrCAD are the more common packages. But this is a process that you will go through. Again, this is a sidetrack lecture. This lecture won't be on the final exam. I'm not going to, but it's things that you need to be aware of 10 years from now. That old American professor we had back there, I can't remember his name, talked about, we had to put pin numbers on these things. That's it. And then actually, when you lay out the board, you have to go one step further. You actually have to tell the software what the footprint of the component looks like, right there. So there is a process of, we do our design on the digital side. In other words, we draw our circuit with all our gates, but somehow we have to get to the physical product. And this is part of that process of fabrication right there. So in this particular case, we're going through the fact that we have an input called clock, shift, and load. We have some outputs. These are going to the pins to the outside world or somewhere else. But we've got a component here, Z1, which is a 74HC04 hex inverter. We also have a quad NAND gate, and I'm using 2 of the inverters on the hex inverter. I'm using 2 of the NAND gates on the quad NAND gate right there. And this is telling me the pins right there. This is pins 1, 2, and 3. And this is saying that I want to tie pin 14 to 5 volts. I don't need to put it down here because on this one here. We don't need to put it on every gate. Just the first instrument that's there. That's our VCC and ground, because and in this class, we draw these, we put these circuits down with gates, and we're going to continue to do that, or we're going to do the same thing with flip-flops, and we forget this VCC and ground thing, right? And I don't know how many times I've taught a basic digital course where I sit there and I draw these circuits, and I go into the lab and they hook them up. Nothing works because everyone forgets VCC and ground. That's it. But they do need to be hooked up to every IC, and that is a mistake. And this is how we do it in the software right there. Now this tells the software when it goes to lay out the PC board to hook up VCC and ground to that IC. But we don't want to draw that everywhere we put that. So, up there. Now, we're going to be using the Cordis capture that. That's a little bit different there. Now, here we've got our clock in, load in, shift, our inverters. We don't bother showing VCC and ground on this particular chip because they're all internal to the IC right there. And that's the package we have there. Now, these are not necessarily pin numbers here. These are just net they call it net numbers right there. Right there. This is pin 1, 2, various things. These numbers really don't mean anything, other than when you get errors. When you get errors, they point to what IC is not connected. Right there. So we're going to be using the Cordis capture right there. And I'm going to kind of skip through the troubleshooting parts right there. Right there. I wish we had a bunch of these on hand, but from what I'm told, we don't have a bunch of these on hand right there. Yep. I'm used to classes where students were actually required to buy these logic probes. These are the most valuable tools for troubleshooting circuits there because you don't have to bother with the voltmeter to measure every right there. Most common internal failures. If you have an internal circuitry, the chip is bad, obviously you're not going to fix that. That's it. And I'm going to skip through some of these up there. I'm just going to put this drawing up here for a second here. A few minutes ago, I was talking about pin numbers, for the 7400, which is quad NAND gate. This shows internally how that chip is connected up there. And as you recall, we were using pins 1, 2, and 3, and then 4, 5, and 6 right there. That shows that's one NAND gate right there. VCC is our pin 14, and ground is our pin 7. That's standard for all 14-pin TTL parts. That's a standard connection. That VCC and ground are connected that way. What they're showing here is that internal to the chip. Now, if you're troubleshooting the board and you find a bad chip, your option is what? Throw the chip away and put a new chip in. You're not going to break the plastic part packaging off and replace the bonding wire. Now, if you're in a factory that does packaging and you start getting bad chips, then of course you got to figure out why the bonding wires are not being connected. And again, I'm just going to go. I'm not going through these slides here. And in a course in technician doing repair, this is always up there. Okay, this is getting back to my next subject here, programmable logic devices. I want to spend a little bit of time talking about those. These are lots of logic gates in a signal IC. I brought in an example the other day and showed it to you up there. Allows the design process to be automated right there. Designers identify inputs, outputs, and logical relationships, and then they're electronically configured. In other words, the software does the design. That's it. We don't get into the Cordis software and we lay out, if we're using the Altera, I think we're using a Cypress Free or Cyrus Free or whatever component we have, the interconnection that there. And I'm not sure how deep these slides go into it. I probably will go a little bit deeper into it, but internal to the chip, this is a very simple PLD right here. And what we've got here, and where's my pen? Hopefully I can get my pen to work. My pen is not working. I think I got a bad battery here. We've got two inputs, A and B, and we go through an inverter here. So we got one line here. This is line A. This is line A naught right there. See that? This is line B. This is line B naught right there. So what we've got here is we've got wires that go across here. One wire here, one wire here, one wire here, one wire here. And quite often, in this particular case, we only have two because we only have two inputs. If we had 4 inputs, we would have 4 wires, usually 4 inputs and gates right there. This term here is we make a connection here, right there. Here we're making a connection here and here. So this happens to be B. This happens to be, it looks like it's B A naught right there. This term right here happens to be A naught. This happens to be B A right there. So we produce these 4 products right there. Right there. So, and we can do that by electronically closing switches right here. Now, depending on the PLD, some PLDs, the older style, they actually put fuses there, and I would blow fuses where I don't want a connection. Right there. I would put it into a programmer, and I would blow the fuses. I would have, here's my 2 lines here, and I'd have a fuse between the 2 of those right there. If I didn't want a connection, I would put a very high current through these wires and make that fuse disappear. Right there. You know, those are one-time programmable parts. Right there. And they're very cheap. Right there. Others use transistors that we can EEPROM program right there. Now what they don't show here is that these then are all ran through an OR gate right there. So we end up with that sum of products notation. But the key thing is we have this switch matrix right there. And we use a programmer to program it. This actually, if you look at this one here, this actually happens to be the Altera board that I brought into class right there. This is a programmable right there. How does system programming that there? Right there. Now the Altera can be programmed in circuit right there. This is typical out-of-circuit programming. We program these chips. Up there. In circuit means that it's done by connecting directly to the portal pins while it remains in the system. That's there. Some components, some parts, PLDs are reprogrammable, some are OTP. OTP means one-time programmable. That's it. The parts that I typically have used in more recent years have been the reprogrammables because I'm only working at the prototype level. When it goes into production, typically you would switch to an OTP part. In the lab, you don't want to keep throwing parts away, so you use the reprogram. But when you go into production, you want to use the OTPs because they're cheaper. Right? You know, the one-time programables are cheaper. They're also faster, smaller, and use less power. That's it. One-time programmables have a lot of advantages in the production unit, but in a design lab, they get expensive and you keep throwing them away. Right there. So, logic circuits. Now, these are the basic design methods that are out there. This class, we're going to be concentrating on schematic entry, right there. Schematic entry means we draw the circuit in the schematic editor and place it into the design. We can use the logic equations. That's not typically used very much. Truth tables and a hardware description language. Probably 75–80% of designs today are using hardware description languages. That's a course all its own. You're going to see some of that there. Because there, and we talked a little bit about that. PLD development can convert any of these descriptions into ones and zeros loaded on the PLD. So in other words, we design the software at a higher level, right there. Now this is out of date. And these slides were not kept up to date. This is now called Quartus. As I said, these software packages all change their names on a weekly basis, right? I kept talking about electronic workbench, and you guys said no, but then you said you use multi-sim, and I thought, yeah, that's the current name. Well, the current name for the Altera Max Plus Plus 2 is Quartus. That's it. So it's a development software package that allows. There are two companies in the programmable logic device systems that are big dogs. When I say big dogs, they're the 300-pound gorillas that dominate that particular industry. If you look at Malaysian-made automobiles, there's only two players, right? How many automobile manufacturers that are Malaysian-owned? Proton and Purdue, right? But they're actually small players when we look at the international market. The big dog in the international car markets are probably Nissan, Toyota, General Motors would be considered a big player. Ford is a big player. Mercedes, BMW. There's lots of players in the automobile industry. But if you look in the U.S., we have three, they call them the big three in the automobile industry. Ford, General Motors, and Chrysler. Those are the three big American manufacturers. Well, in the PLD market, there are many, many players out there. The two big ones are Altera and Xilinx. Right there. That's there. And they've been around for about, Altera is a relatively young company. They've been around since the 1980s, late 80s, I'd say, maybe early 90s. Xilinx is a little bit older. Xilinx is the bigger of the two companies, but they're the big players in that area, right there. Most academic people that teach tend to use Altera because it's a little easier for students to grasp. Most people that do this stuff for industrial use tend to use the Xilinx package. The design tools, the languages and everything else are similar enough. If you learn one, you learn the other. That's there. Plus, Altera I've been working with Altera for many, many years. Playing with lights there. That's there. So I've been using Altera since day one, the first version. So I'm very familiar with the Altera software. I've used Xilinx for other things. Which lights are you? I'm going to try to ignore you. That's there. Okay. So we get into this whole description of these are the tools. So you're going to see this Altera quite a bit here, up there. And when we set up some labs, you'll be using the Altera packages for that. We may be sharing boards. Okay. We end up with something called hierarchical design. Hierarchical design means that we can design subsystems and tie them together into a larger system. This is a theoretical concept that makes perfectly good sense when you have a large project. If I'm designing the new Intel i7 processor, which, trust me, is a custom IC design using digital design techniques, microprocessors are not designed by using microprocessors. It's a digital finite state machine design using these techniques right there. And I've taught courses and I've assigned projects in the past where people had to design a basic microprocessor using these techniques. But microprocessors start off by using as a digital circuit right there. So if I have to design that, I've got a team of 100 engineers up there. I'm going to break it up into pieces, right? This team over here of 4, you're going to be working on the memory interface. This team over here, you're going to be working on communicating to the graphics card. This team right here, you're going to be doing math processing. This team here, you're going to be processing, the disk, talking to the hard drives, the various serial ATA drives, or this group in the back is going to be working on new, the newest, greatest, what I want to say, solid state drive interface right there. So we've got all these various parts to our project right there. We break them up into pieces, and we assign them. We can use different design techniques for different parts. It might be easier if you're going to be interfacing the memory to work on the timing pattern and tell the software what the timing pattern has to be to talk to that there. It may be easier for this group over here to draw schematics. This group over here is going to be working in VHDL because you're doing math processing and you want to do it at a very high level. You want to write something, use that there. HDL doesn't exist anymore. They dropped that. But we can put Verilog here. We may have a group doing a Verilog pattern. We'll just say this is Verilog instead of VHDL to HDL. But these are different design tools that we have available at our. They all have a different skill set. It's all a little bit different, but they can all be tied together. Right there. Probably 75-80% of the work that I've done has been using VHDL. That's there. VHDL is a high-level hardware description language. That's it. It looks a lot like C code, or actually more like Ada, but it looks a lot like code, computer code, but it's not a computer code. HDL was a language developed by Altera, and it stands for Altera Hardware Description Language, right there. VHDL stands for Basic Hardware Description Language, and Verilog stands for I don't know. Those are the. And then there's also ways where translators will translate from C to hardware description. So, but the whole idea of the hierarchical is that we can design small circuits and combine them into a large circuit right there. It also allows us to reuse parts of a circuit right there. Well, top down is here is an example of a large system. This is a DVD player right there. And we're going to design a custom chip to do that. And we've got all kinds of various parts to that. And again, this particular lecture really is kind of a side note, getting away from the nuts and bolts of what we're doing. We're kind of getting into the theory a little bit. But here we have a top level system. We have three major parts. One is how do we spin the DVD? How do we run the laser to track it? And then how do we process the signal and convert that back to audio right there? We have three major subsystems in this DVD system right here. So we got our track decoding, that's there, and we got our disk speed control loop. So in other words, depending on what track we're reading, and if you look at a DVD, if we're reading the outside track, we have to spin slower than if we're reading an inside track. Because the number of bits we need to read has to be consistent. We have to, that's there. So as you move your laser in and out from the center of the DVD to the circumference of the DVD, you have to modify the speed in which this DVD spins. Because as you look around, this circle here is larger than this circle right there. So if they're spinning at the same speed, I'll cover this much of this circle and this much of this circle right here. So I have to vary the speed according to where I'm at in the DVD. That's there. That's what this does right there. It looks at where we're at, what track we're reading on the DVD, and then adjusts the speed accordingly. That's this team over here doing that. This team right here is now looking at positioning the laser That has a drive motor. It has to detect whether there's any skips or misses that there. And then it's got to decode the pulse train as it reads the laser. Well, this pulse train is then sent to the audio-visual select team that then is going to go through and do the parity checking and all the other analog process. Now, this part here is probably going to be a separate IC. That may be a separate team because that's going to be that team there is the analog part right there. So that's going to be off the chip. But you can see as we're looking at a typical DVD player, we have to break it up into smaller pieces. This is this top-down design technique. And I'm hoping that you've seen this type of discussion before. If not, that's fine. You'll see it again, right there. But this is the way that when we design a system, we have to look at it from the system perspective. That's it. I can't grab a DVD, design a DVD player from scratch, from the beginning. I have to break it up into subsystems. And when we look at a subsystem, then that goes back to our subsystem goes back to our hierarchical design, because each one of those then goes into this top-down design. So the two of those go hand in hand. You'll hear the terminology right there. Again, this goes back to our programmable logic devices in the fact that we're able to use these techniques using a software package like Quartus. Or, I can't remember the language. I have it at my desk, though I think I threw it away, actually. That's there. I have used it. Okay, timing simulations, we've looked at that there. I'm going to kind of skip through that there. This is kind of a software package right there where I'm not going to go through this in great detail. I've run my hour, but I'm going to go ahead and finish out these slides here. That's there. We do our design, we create our design file, we compile it, and I went through this process the other day when I ran the demo. Are there any errors? I think I did have an error. I had one pin that is not connected. I go back there. I simulate it. If it simulates right, great. If the simulation's wrong, I go back and I modify my design. Right there. I create the output file, I program the PLD, and then I test it. Right there. And as you recall, I did a very simple 4 input and/or circuit there, and I went to the point where I was flipping the switches to verify that it worked. Right there. So this is a typical design process, and inshallah, you'll be going through this process with some projects here, right there. Okay. Every programming language has a unique that there. I'm not going to dwell on this right now. I just want to kind of look at. This is the one that's the most commonly used in the U.S. and Europe. It's the one I'm most familiar with, so it's the one I'm going to talk about. Unfortunately, you got an American instructor that's worked for U.S. defense contractors, and I know VHDL. I don't know Verilog. A little bit of a history is VHDL stands for Basic Hardware Description Language. The VISIC project was a project funded by the U.S. Department of Defense. That's there, which is a big gorilla when it comes to the electronics industry. Not only in the U.S., in the world. They spend a ton of money developing electronics and doing electronics research. They're probably the number one in research funding agency in the world in terms of electronics. Most people don't realize that, but that's just the fact. And I've worked for multiple defense contractors. That's there. So when they put money into a project, they expect returns on it. So they require that any vendor that does any work with the Department of Defense to use VHDL. Because of that, almost all electronic design companies in the U.S., UK, Australia, Germany, Norway will use VHDL. All the big NATO companies out there, Israel, out there, anybody that works for the U.S. Department of Defense. People that don't work for the U.S. Department of Defense prefer another language called Verilog. And that's what you're probably going to see more often in Southeast Asia is Verilog when you look at design. The two of them are like C and what's another language? C++. I mean, they're similar enough that you can go back and forth. So my example is VHDL won't hurt you. Looking at the same code in Verilog is close enough. My battery's starting to go bad here. Got a real loud announcement, battery low. So that means we're running into my time here. So, okay, that's there. So I'm not going to get into representing data in the VHDL, but that's there. So syntax, right there. In other words, let me just kind of put that there. This basically declares that we're going to have an 8 input right there. It's going to be ordered high to low right there. And I'm going to kind of VHDL, I'm going to jump into right there. This is how you would define an input port right there. It's a bit vector, 7 down to 0 right there. Then it's an 8-bit port right there. We can also define bit vectors internally as a signal right there. And we have all types of different combinations of it right there. And I know I went through these slides on the one that I put up online, but I probably didn't cover them any more detail than I am now, because the goal here is not to teach you VHDL. You're not going to be writing VHDL code in this class. You're going to see examples of VHDL, but I'm not going to spend a lot of time on that there. Here's an example, though. This is a good example of why, and this happens to be an AHDL, it's not VHDL, but this kind of shows you real quick why I don't spend a lot of time on Karnaugh maps right there. Here I've got a 3-input truth table, and AHDL, which is up there, has a function called table right there, where I put in my truth table exactly the way it is right there, and I just tell the software to design the circuit. I don't even have to look at this right here. I don't have to do the Karnaugh map right there. I just put in the truth table and let the software do the design right there. And as I said earlier, we're looking at circuits with millions of gates today. Design techniques designed for circuits with 10, 15 gates don't work. So now we've got the option of just putting the truth table right into the software right there. And this is an AHDL right there. As I said, there's 3 different languages. AHDL is an obsolete language, but there's the same code in VHDL. You see, it's a little different, but the format's the same. We have with embed select, and here's our, here's our 0 through 7 right there, and this is our output right there. In Verilog, I don't have the same circuit here or code with Verilog. Would look like that. As you can see, they look totally different. So if you learn one, there's a learning curve to go to the next one. But once you learn the techniques with one, going to the next one is fairly easy. And one of the things I should say to everyone in this room, I have learned over my 30 plus years since I graduated with my undergraduate in engineering, that I've had to learn probably 10 different programming languages and probably 4 or 5 different hardware description languages. Whatever language you learn between now and the time you graduate will not be the language you'll be using 5 years from now. These languages change on a regular basis. C has been the most popular language for the last 5 years or so in the microprocessor world. But now that we're seeing things like the Raspberry Pi and the Arduino, we're starting to see Python pop up as a language. That's there. So languages are changed on a regular basis. So that's why I'm not going to spend a lot of time looking at these languages in great detail. That's there. And we can have if, then, else structures right there. Again, if, else, again, it looks like C. There's the same thing in VHDL and if, then, else right there. As you can see, looking between the two of them, they look different, but they do the same thing right there. And we can get all kinds of various combinations right there. This is an example for a temperature control, too cold, just right, too hot, right there. And again, there is in VHDL, we're looking at an if-then else structure right there. And I think I'm probably going to have to stop right here. This is our case construct right there. Again, I'm not really interested in going through this in great detail right there. So let me end this at this point. Right there. There's a possibility